somewhere around almost every star, there may be a narrow region where conditions are not too hot and not too cold. Astronomers call it the habitable zone. You may know it by its more famous nickname, the Goldilocks zone. The idea sounds simple at first. If a planet orbits close enough to receive warmth, but far enough away to avoid being roasted, then liquid water might exist on its surface. And because liquid water is central to life as we know it, this zone has become one of the most important guideposts in the search for worlds beyond Earth. But the habitable zone is not a promise of life. It is only a starting point, a cosmic filter that tells scientists where to look first. The reason liquid water matters so much is not because scientists lack imagination. Life elsewhere could be strange, unfamiliar, and built on chemistry we have not seen before. But on Earth, every known living thing depends on water. Water is a powerful solvent, meaning it can dissolve and transport the chemicals life needs. It stays liquid across a useful range of temperatures, and it helps complex molecules interact in stable ways. So when astronomers search distant star systems, they often begin with a practical question: could this planet have surface water in liquid form? If the answer is possible, the planet becomes more interesting. If the answer is no, it does not rule out all life, but it makes Earth-like life much harder to imagine. The inner edge of the habitable zone is controlled by heat. If a planet orbits too close to its star, it receives too much energy. At first, that may only mean hotter oceans and a stronger greenhouse effect. But beyond a certain point, the situation can become catastrophic. Water evaporates into the atmosphere, and water vapor itself is a greenhouse gas. That traps even more heat, causing still more evaporation. In the most extreme case, a runaway greenhouse effect can boil away the oceans and leave the planet dry and hostile. Venus is often used as a warning example in our own solar system. It reminds us that distance from a star, atmosphere, and heat balance can decide the fate of an entire planet. The outer edge of the habitable zone is the opposite problem. A planet that orbits too far from its star receives too little energy. Its surface water begins to freeze, and ice reflects more sunlight back into space, making the planet even colder. A thick atmosphere rich in greenhouse gases can help by trapping heat, so the outer edge is not a simple line. Carbon dioxide, pressure, clouds, and planetary geology all matter. But there is a limit. Eventually, even a strong greenhouse effect cannot compensate for weak starlight. Past that point, oceans would remain frozen on the surface. The world might still hide water beneath ice, but it would no longer fit the classical idea of a surface habitable zone. This is why the habitable zone is not just about distance. It is about the relationship between a star, a planet, and an atmosphere. A bright star pushes its habitable zone farther outward because planets can be warmed from greater distances. A dim star pulls the zone inward because a planet must orbit closer to receive enough heat. The planet's atmosphere then changes how that energy is stored or lost. Two planets at the same distance from similar stars could have completely different climates if one has a thick heat-trapping atmosphere and the other has almost none. So when scientists say a planet is in the habitable zone, they are not saying it is Earth-like. They are saying its orbit makes liquid surface water physically plausible under the right conditions. The phrase Goldilocks zone comes from the fairy tale of Goldilocks and the Three Bears. In the story, Goldilocks rejects things that are too hot, too cold, too large, or too small, and chooses the one that is just right. It is a useful metaphor because the habitable zone sits between extremes. Too near the star, and water can be lost to heat. Too far away, and water can freeze solid. In the middle, there is a range where surface water may be stable. But the metaphor can also mislead. Space does not offer one perfect orbit. The habitable zone is a shifting band with uncertain edges, and what is just right depends on the planet's size, atmosphere, clouds, rotation, and geological history. The habitable zone became especially important after astronomers began discovering exoplanets, planets orbiting stars beyond the Sun. Many detection methods can estimate how far a planet orbits from its star. That makes it possible to ask whether the planet sits inside the region where liquid water might exist. The Kepler Space Telescope transformed this field by finding thousands of candidate planets and showing that planets are common in the galaxy. In 2013, astronomers using Kepler data estimated that there could be tens of billions of Earth-sized planets in the habitable zones of Sun-like stars and red dwarfs in the Milky Way. That number did not prove life is common, but it changed the scale of the question. One of the most famous examples is Proxima Centauri b, the nearest known exoplanet in a star's habitable zone. It orbits Proxima Centauri, the closest star to the Sun, only about 4.2 light-years from Earth. On paper, that makes it incredibly exciting. It is nearby by cosmic standards, and its orbit places it where temperatures could allow liquid water if other conditions are favorable. But Proxima Centauri is a red dwarf, a small and active star that can release powerful flares. A planet close enough to be in its habitable zone may face intense radiation and atmospheric erosion. So Proxima Centauri b shows both the promise and the caution of habitable zone discoveries. Location is important, but it is not enough. Many planets found in habitable zones are not Earth twins. Some are super-Earths, meaning they are more massive than our planet, while others may be gas giants. This happens partly because larger planets are easier to detect. They pull more strongly on their stars and block more light when they transit in front of them. But a planet being massive, or even being inside the habitable zone, does not automatically make it suitable for life. A gas giant has no solid surface like Earth, though its moons might be interesting. A super-Earth could have crushing gravity, a thick atmosphere, or a volatile climate. The label habitable zone planet is therefore not a final verdict. It is an invitation to investigate more deeply. Moons add another layer to the story. A giant planet in the habitable zone might not itself be habitable, but large moons around it could be. In our own solar system, moons like Europa and Enceladus are already interesting because they may have subsurface oceans, even though they are far outside the Sun's classical habitable zone. Around other stars, a planetary mass moon orbiting a gas giant in the habitable zone could receive warmth from the star, tidal energy from its planet, or both. Some scientists think habitable moons might even outnumber habitable planets. Detecting them is extremely difficult, but they broaden the search. The best place for life may not always be the obvious planet in the spotlight. There are also important limits to the classical habitable zone concept. It focuses on surface environments powered mainly by starlight. But Earth itself contains deep biospheres, communities of organisms living underground or near hydrothermal vents, where sunlight is not the main energy source. If life can survive in such environments here, then worlds outside the classical habitable zone might still host hidden ecosystems. A frozen moon with a subsurface ocean could be biologically interesting even if its surface is lifeless. Scientists have also proposed other zones where liquids besides water could exist, supporting hypothetical alternative biochemistries. These ideas are more speculative, but they remind us that the habitable zone is a tool, not a complete definition of habitability. So what does the habitable zone really tell us? It tells us where Earth-like surface habitability might be possible. It helps astronomers prioritize targets in a galaxy filled with planets. It connects a star's brightness, a planet's orbit, and the possibility of liquid water into one powerful concept. But it also forces humility. A planet can sit in the habitable zone and still be sterile, frozen, scorched, airless, toxic, or unstable. Another world outside the zone could still hide an ocean under ice. The search for life is therefore not about finding one magic distance from a star. It is about piecing together many clues: atmosphere, temperature, chemistry, geology, radiation, and time. The Goldilocks zone is where the search begins, not where the mystery ends. If you found this helpful, please like this video and subscribe for more explainers.